We have this sound wave of the form E is equal to 60 cos 1800t minus 5.3x, where E is the displacement that's expressed in micrometers, t is in seconds, and x is in meters. So we need to find what is the ratio of displacement amplitude to the wavelength. So here we are comparing two distances. So one is the amplitude of the particle, second is wavelength of the wave. Second part, the velocity oscillation amplitude of the particle and its ratio to the wave propagation velocity. So again we are taking the ratio of the velocity of the particle and velocity of the wave. Third part, the oscillation amplitude of relative deformation of the medium. So if you don't know what is relative deformation, it is like strain. So in a strain, if you take any length of a rod, let's say, so whatever is delta L by L in that rod will be relative deformation of the rod. So it is independent of the actual length of the rod, because that's a ratio of delta L by L. So here also we need to find this. So we'll see more of this relative deformation in detail when we do C part. So let's do A and B. So A wants us to find the amplitude of the displacement divided by wavelength of the wave. So wavelength will be 2 pi by k. K from here is 5.3. Amplitude is 60, which is in micrometers. So it will be 16 to 10 to the power minus 6. So we take this ratio and that comes to be 5.1 into 10 to the power minus 5, which is a very small number. So you can imagine that in a traveling sound wave, the amplitude of the particle that is disturbed is very, very small compared to the wavelength of the wave. So therefore, amplitude of the sound wave is quite small relative to the wavelength. But when we plot this y versus x, so you know we plot it quite comfortably. So, but our typical wave graph is also on a heavily distorted scale. So here you can see that this amplitude and the lambda are of the ratio 1:1, but actual ratio is 5.1 into 10 to the power minus 5. So realistically, this ratio, so if you take the man's height as the wavelength of the wave, then amplitude of these particles that are vibrating, that will be the diameter of a man's hair. So this is the actual sine graph of displacement versus x. So this diagram is there for the feeling of it. So if wavelength is our height, that is 1.5 meter, that is 200 hertz. I mean, so when sound wave is traveling at 200 hertz, the wavelength will come to be 1.5 meter. Then amplitude will be of the size of our hair thickness, that will be 100 micron. So just to get you a feel of it, that in sound waves, this amplitude is quite small. Now for the B part. So here we need to find the ratio of the velocity, amplitude and the and the wave velocity. So we know the maximum velocity of the particle will be omega A. So A is here and omega is here, so that comes to be this. So it's 10.8 centimeter per second. So you might be thinking it's quite good, quite high, but then we see the velocity of the wave, that is omega by k. So in this case 1800 by 5.3, that comes to be 340 meter per second. So quite close to our speed of the sound. So now if you take this ratio of velocity of the maximum velocity of the particle divided by velocity of the wave, you can see that also comes quite small. So again, the velocity of the particle is minuscule compared to the velocity of the wave. So now let's attempt this third part. So in C part, we need to find the amplitude of relative deformation and its relation to the velocity amplitude. So this is our original wave. So first, just a quick word about the relative deformation. So that's defined as deformation per unit length. Kind of like a strain, where if you remember, that was delta L by L. So that too was deformation per unit length. So here we have to consider the deformation per unit length. So let's take a length first. So let's take a length of dx. So the particle here is at a distance x and the particle here is at a distance x plus dx. So these are two nearby particles at location x and x plus dx when particles are at rest. Now when wave passes through them, let their displacements be s and s plus ds. So let's say this particle displaces by s and this particle displaces by s plus ds. This is the undeformed state when the particles were at rest, and this is when particles are deformed. So now relative deformation is deformation per unit length. So that is displacement of this particle minus displacement of this particle upon length between them. So again, you can imagine that if it is a rod, if this moves by 2 centimeter, this moves by 1 centimeter. So the deformation, actual deformation in the rod will be only 1 centimeter. So just like that, this particle moved by s plus ds, this particle moved by s. So actual deformation will be s plus ds minus s. Divide by length, that is dx. So this is our relative deformation, which comes to be, so s will get cancelled, it will be dou s by dou x. So why dou? Because we are talking about one particular time. So if we do dou s by dou x here, that comes to be ak sin omega t minus kx. So here ak is the amplitude of relative deformation. That is the answer of first part. Now they want us to relate it with the velocity oscillation amplitude. So to find the velocity, let's differentiate this with respect to time. So dou s by dot a will be minus a omega sin omega t minus kx. So here a omega is the amplitude of velocity, which he wants us to relate with relative deformation. So you can already see that sin omega t minus kx term is there in both. So let's just divide 2 and 1. That will give us dou s by dot a is equal to minus omega by k dou s by dou x. And we know omega by k is velocity. So that gives our one of the differential forms of wave equation, that is dou s by dot e is equal to minus v dou s by dou x. So this is the relation. So dou s by dou x is relative deformation and dou s by dot e is the particle velocity and v is the wave velocity. Quite an important relation. All right.